this very interesting audience that's here as well. Actually, before I give any talk, I usually walk around the aisles asking people, why are you here? Because everyone comes with a different interest, a different motivation, a different background. And I understand that there's a lot of interest in having some very seriously difficult mathematics in this. And there will be, don't worry. But at the same time, I understand that there's some people in the audience who maybe are not necessarily looking forward to that part the most. And so that will not be the entire talk. So I'll blend the two. Actually, I decided to open with maybe a little bit of a historical background of even how I came here, but that will also help to connect between what these Olympiads are and maybe what some mathematicians do, maybe what some of you do as well. Maybe the beginning of the story is the last time the United States team won the International Mathematics Olympiad. And this is something that affected me very much because I was growing up in Madison, Wisconsin. It's a city in the United States, which is not New York. And just to say the least. And I have not heard much about mathematics being a sport. I should say that as an impressionable young tween, or as they're called, I was used to thinking of sports as athletic sports. And to find out that you could actually try to do mathematics to very high levels, this was very inspiring to me. In that sense, I should say a big thank you to G Research for being the gold sponsor of the International Mathematical Olympiad this year. You may have changed certain people's opinions about whether mathematics can also be done to extreme intensity. The blinking of the screen, I don't exactly know why it is, but we can pretend it was for dramatic effect. But this particular result happened to make the United States newspapers. And in general, when something like this goes to newspapers, then more people, including people in Madison, Wisconsin, learn about it. At the time, I thought I would never have anything to do with it, because I was just some kid going to middle school there. Unfortunately, I did have something to do with it. And I was involved in another story, which is the year that I actually went to the International Mathematical Olympiad in 1999. That's where I met one of your colleagues, Ben Henry, actually. Yes, I met him in 1999. And unfortunately, we were the second worst ever. I should say this is actually fake news. I made up the Onion article. The headline is true, but the article is false. On the other hand, I use the Onion to maybe say two things. One is, in case in this country you do not know, the Onion is a satirical magazine, so never quote them. Number two, the Onion was actually founded in Madison, Wisconsin, which is the city I grew up in. So we are known for something. But after this, I said I would probably never ever be involved in such things again. And I decided to move on to maybe higher mathematics, research mathematics, and so on. As I was studying, at some point, I decided to come over to your part of the world. Some of you may know what this is. I don't know how many of you did Part 3 at Cambridge. This is, in the year that I did it, they threw the results off the balcony when it was announced. Is this what always is done? Yes. Okay, so apparently this has been and will be and so on. Well, thank you for helping to fix this. Right, so I came here to do Part 3, and during that time, I had the opportunity to try to discover that combinatorics, which was the subject that I was doing, was not just Olympiad combinatorics problems, which might look like where you just have to be clever and combine the pigeonhole principle with counting things in two ways. And that was about it. Right? We learned actually when we were doing combinatorics as young mathematicians that it was maybe a very ad hoc subject where there wasn't much to it. Where if you, on the other hand, if you wanted to be a glorious number theorist, there would be much, much more. All of these problems would involve much more to solve them. However, after studying at Part 3 and taking a class in probabilistic combinatorics and other interesting classes here, I then went on to do a PhD with a remarkable PhD advisor who taught me about what Paul Erdős did. This is a quote of Paul Erdős. Paul Erdős is a very famous mathematician who is known for saying many things, including television is something the Russians invented to destroy American education. He also is one of the most prolific mathematicians of the last century, who did enormous numbers of collaborations and invented ways to solve combinatorial problems using ideas that might come from other parts of mathematics. I might make some comments about television and education at some point later, especially if you have Q&A about how that factors in with the greater society that we live in. But my PhD advisor, Benny Sudipal, then went on to teach me other things as well, which is where we're about to move into a problem that I want to talk about today. You see, when I went to start my PhD, I had this background of maybe Olympiad mathematics, and we would try to be clever to try to solve things. At some point, he said to me, you have to remember things. You can't just invent everything on the spot. And this was very interesting because I should say back, what I always had done before was always improvisational. When I was doing any kind of math problem, I would just use my bare hands, fight a little bit, and maybe the thing would fall apart. But he said if you want to make any sort of impact in the world of knowledge, you actually have to remember things. You have to build on top of what other people have done. And so that brings to the story of a particular question which I happened to run into. The year is 2008, and I had been away from the maths Olympiad for quite a while. I actually had gone on to be a PhD student. Actually, I had kids. I even worked at a financial firm for 2 summers, D.E. Shaw. And at some point, I decided to maybe get involved with math Olympiads again. And when I decided to get involved again, then I became a marker for the United States Math Olympiads exam. So this is the exam where there are 6 questions. People write long scripts proving some statement. And I guess that is a significant amount of work. So the first thing that you do if you want to come back and help at the Maths Olympiad is you help to mark the scripts. So I said, okay, I'll be happy to do this. And I came. And I happened to see that that particular year I was brought back to help mark the scripts, there was a remarkable problem. And this is a problem from the 2008 United States Mathematical Olympiad exam. It was not stated this way. It was stated in terms of friends and numbers of handshakes or something. And again, because now I understand the audience is not all mathematicians, I will attempt to translate some of this back to normal English, right? So what this is a graph is basically a network of nodes. You can think of that as people. The context of this problem is in any room of people. That's what for every graph means. If you want to know how many ways, we can split this room of people into 2 parts, where some people go there and some people go there, such that in each part, the number of friends you have in your part is even. That's the goal. We want to split the people into 2 parts so that in each part, everyone has an even number of friends in their part. The number of ways to do this is a power of 2. This was the problem 6. And to put some context on the internet, on these Math Olympiad problems, problem 6 is typically the hardest problem in the mathematical Olympiad, usually. I want to dwell on this question a little bit before we start talking about how to attack this. First of all, this is a very strong condition. So by the way, by this point, maybe you can tell we've moved from stories into solving some math problem. But I will still try to make the math problem discussion as understandable to as wide an audience as possible. In fact, the only hardcore mathematics I will use will involve something that is usually taught in high school, but in a clever way. Right. So when I start dwelling on this problem, it's a really strong condition. Imagine you're trying to do this. Imagine you're actually trying to split the room. Then every single person has to answer to you, do I have an even number of friends in my part? In fact, if there were n people, there are n conditions to satisfy. That's actually what makes this hard. If I only had one condition to satisfy, called maybe the number of friendships in total on one side has something, that's easy to count in one go. But we unfortunately have to satisfy many things. In fact, for this question, proving something is a power of 2. Just as a refresher, the smallest power of 2 is 2 to the power 0, which is not 0. It's 1. And in fact, even trying to find one way to partition everyone is not trivial. So this has 2 layers of complexity. One layer of complexity is we have to find a way to do it. The second layer of complexity is somehow it's a power of 2. But I should actually say, in this case, by adding the 2 layers of complexity, the problem actually became easier. So this is a little bit unusual. Usually if you put more complexity, you may think that the question becomes harder because you have more to do. On the other hand, if you actually add another layer of complexity, sometimes that indicates towards what you might need to do to solve it. Okay? But this is a story. And what does this have to do with me studying my PhD? Well, as I was a PhD student, I was working with a very intense PhD advisor who was of the opinion that if you want to learn something properly, you would grab the book and you would do every single problem in the book. This is true of, actually I would say this is a very effective strategy. I also employed this even before I met him. And so I happened, right at this time, to be following his suggestion to learn a subject called graph theory, where you basically study these kinds of networks in great detail. And so I was reading a book, it was a German book by a person named Listo. It was called Graph Theory. Standard text, actually, that you use to learn graph theory. And when I saw that I was going to mark this question, I had just come across the following exercise. It's called Galois cycle-co-cycle theorem. And it says that there's a way to do this. not supposed to have a math-Olympiad problem, which is related to an actual result. But this is also maybe making a comment that whenever we come up with math-Olympiad problems, or whoever comes up with them, that person can't possibly know everything that there was to know in the whole world about mathematics. So it sometimes happens that there's actually some higher tech stuff that you can use to possibly do better at the International Mathematical Olympiad. This has something to do with actually how we run part of the United States Math Olympiad training, which I'll make some comment about later, about how effectively, if you think about mathematics not as a high school mathematics or primary school mathematics, secondary school mathematics, and so on, but you think of it all as a big unified discipline, you can actually often make connections that you may not have expected. But this stays, that it's possible. Now this question, actually, I remembered, because it had been burned into my head from me attempting to solve this for an inordinate amount of time and failing. So this is actually a very hard question. This was actually one of the asterisk questions in the book. But I want to attack this question in today's talk, because this is an example of a question which looks actually like something you could explain to anyone from the street. If I went on the street and said, I'm trying to divide everyone here into two parts so that everyone on this side has an even number of friends on their own part, everyone would say, I understand what you're talking about. They might ask you, who cares? But that's a separate issue, right? I can answer for you, who cares? The reason why we should care is because this result turns out to be one of the most interesting applications of a certain technique from linear algebra. And in fact, the reason I was so fascinated by this question when I came across this was because there was actually a line of research of how you could solve this problem without bare hands. You see, this question was in the early stages of a book, because there is one way to do it just with some induction. And you just kind of do it, and you don't feel like it's that great, and you don't really understand what's going on. But there was a remarkable discovery by a mathematician named Pierre Caro, C-A-R-O, where he found out that you can use the techniques of matrices and equations to try to solve this problem. Except that we have this word even. So what I intend to do is I intend to be talking about how you might use equations and linear algebra, not over the real numbers, but over a different field. Just a quick gut check. How many people have I lost so far? So how many people are still with me? Okay, so we will keep going. So you can work over the even and odd numbers. You can actually solve systems of equations where I don't say my number is a number, I say my number is a 0 or a 1. 0 if it's even, 1 if it's odd. The problem is you can't actually hit it quite from there. The story actually adds one more layer. It turns out to be easier to attack this from a result that was proved by a colleague of mine at Carnegie Mellon University. At the time that I came upon this, he was only a future colleague because I was a PhD student. I want to say a little bit about this result, and then maybe go back to these strange abbreviations out higher. So this thing is a problem that sounds like maybe a fun puzzle, a puzzle you might be able to ask a high school student, which says that suppose I have a network, meaning I have a bunch of nodes, I have a bunch of pairs of nodes which are connected by these edges, and every node has a button which turns its light on and off. Except that the button is powerful. It does not only turn on the light, it doesn't only toggle the light that it's sitting at, it also toggles all the lights of any other node which is connected directly to it. So you can imagine that you're pressing these buttons, and this is changing certain chunks of lights at the same time. The result is that if you start off with any network in the entire world, and all the lights off, there is a way to turn them all on. If not for the fact that the switches were powerful, this would be a trivial result. If it were true that every button would toggle its own light, I would just simply press every button, one after the other, and I'm done. Unfortunately, there's an enormous amount of interference that happens when I hit different light switches. So, I don't know what's going on. I think we're okay. We're okay with the flashing, I think. I'll just pretend it was intentional. So, it actually, ironically, it worked fine with no flashing until now, but that's fine. So, it's like lights, right? So when we're talking about lights turning on and off, but really what I did is I just pressed this, and the screen went off too. Right. So now, for this particular result, I now want to hit this. And I want to talk a little bit about some linear algebra that you might use to try to solve this question. The first time I saw this, I was quite fascinated that you could do such a thing. And at this point, I'm actually not going to use these slides anymore because you can't really teach mathematics through slides. I actually always found out that mathematics made the most sense when you switch to the chalkboard. So I'm going to switch to my board now. And for the next part of this talk, I'm actually going to just entirely write on this because I always felt that math made more sense if you were able to see it come in real time. So in this particular question, what we have is we have a graph. And the graph has the property that some of these, well, every single one of these nodes happens to have a switch. And the switch can turn all of the lights on the node and around the node on or off. Once you say the word linear algebra, the first thing you should do when you have a graph in linear algebra is to look at a particular matrix. In fact, there are often two matrices. I'll take one of the ones which is the simplest. And the matrix that you look at is called the adjacency matrix. It's okay. It seems like the flashes are short enough that we don't have to worry. The adjacency matrix of the graph looks like this. Again, this is something you guys may be familiar with, but I will just simply state it again because it can serve as review or it can serve as an introduction to other people. What you do is for each of the vertices of the graph, if I gave each vertex a name, like 1, 2, 3, 4, 5, 6, the adjacency matrix for this particular graph will be 6 by 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And what you do is inside the adjacency matrix, if you have 1 adjacent to 2, which you do, then you put a 1 at the spot where 1 and 2 are, and a 1 at the spot where 2 and 1 are. So this is just a way of encoding what this network looks like. On the other hand, 3 is not adjacent to 4, so where 3 and 4 come, I'll put a 0. So this is row 3, column 4, and so on. Does this notion make sense? This is adjacency matrix. All we're doing is we're recording who is adjacent to who. And this is a certain way of storing actually your information about the graph. Now, if you're trying to do something with adjacency matrices, it turns out that there are many different kinds of algorithms you can run on them. For people here who are more interested in practical computer science, if you haven't seen this before, you can use adjacency matrices and take their eigenvalues to learn lots of things about your graph. For example, if you were going to take a random walk, what does it look like if you walk for long enough? Actually, that might be a twist on the adjacency matrix. But what I just said is the heart of a multi-billion-dollar algorithm called Google's PageRank. But anyway, then we'll go back to our pure mathematics world. And if I have this adjacency matrix, I'm trying to solve a problem. I'm trying to find a way to touch some of these switches so that the net result of touching some of these switches is that all the lights are on. Whenever I'm trying to do something like that, I would like to encode my list of which switches to touch as some kind of a vector. It seems quite reasonable. So far, this is actually quite a reasonable idea. What you could do is you could say that there's a vector of which switches to toggle. And I could try multiplying these. This is how I'm going to write my matrix product. So I have a square matrix multiplied by a vertical matrix with exactly 1 column. If I multiply these, what does that tell me? Is that actually useful? Right now I'm showing the knee-jerk reaction of what you try to do if you attempt to use some kind of linear algebra to solve this question. For example, if what I decided to do is just for fun, let's toggle switch 1, let's not toggle switch 2. Actually, let's not toggle anything else. I'll be lazy. That's what this vector means. If I write a 1 with a bunch of zeros, what that means is I only toggle switch 1. This might be interesting to try to multiply these matrices to see what happens. And if I multiply these matrices, you will get a column vector, which has only 1 column. And in this particular case, this is actually a relatively easy matrix product to make. In fact, it might not even be very interesting. So when I look at this, if I'm doing a matrix product, since I have a 1 and a whole bunch of zeros, when I multiply matrices, that 1 is just going to hit against whatever's in the first column. So for example, the result of the first multiplication is 0. The result of the second multiplication is 1. Are people with me so far? It's 1. And if I keep going, I basically need to know what is that first column. And in that first column is telling me what is adjacent to 1. So if I was to fill out the rest of the first column, in this case, I'll get a bunch of zeros. And so here, if I multiplied, I would get this. To be honest, I'm just doing this slowly right now, just to warm up to this idea of multiplying matrices, and then we'll keep adding more sophistication as we go. What this is telling me right now is fairly useless. This is just telling me that if I press 1, well, nothing. This doesn't even tell me what happens if I press 1. Because actually, if I press 1, what should I see as my lights? 1 and 2. And it looks like if I multiply them, I only have a 1 in position 2. But fortunately, there's a way I can fix this. It's not to use the adjacency matrix. What should I do? Let's call the adjacency matrix A. What should I do instead of an adjacency matrix? There's something I can do where I still want to do the same product. But instead of A, I adjust it a little bit. And I want to make it so that when I multiply it by 1, 0, 0, 0, 0, 0, I would like that my result is something like what happens when I actually press the button on 1. I would like that I get 1 and 2, both on. Is this okay with people? How can I adjust my A? Add the identity matrix. So what I do when I add the identity matrix is I simply make it so that on the entire diagonal, I have 1s. 1, 2, 3, 4, 5, 6. By the way, I should emphasize when you have an adjacency matrix, normally the diagonal has no zeros. The diagonal is all zeros because no vertex is adjacent to itself. And so, if I took my A plus I, then I would get something like this. 1, 1, and then these were all zeros. Are people still with me? So this is interesting. I now seem to have a machine. If I take A plus I, and I multiply it by the vector of pressing 1 button, what comes out is the length situation. But that works even better than just pressing 1 button. Because if I do everything where if all calculations are over F2. F2 means zeros and ones, where I say that 1 plus 1 is 0. If I make all calculations over F2, then it turns out that if I took A plus I times anything, times any vector of zeros and ones, which maybe we'll call x, then this, the output state, is actually always going to be the state of the lights. So this thing here will be exactly the lights. Okay, here's a quick check. How many people do I still have with me right now? Okay, good. So then we will just keep going at this pace. Right. So A plus I times x equals the lights. So what do I want to solve for? In this particular result by Sutler, what we're trying to do is we're trying to prove that there is a way to adjust these light switches so that the output has all ones. So I would actually like that the result of all of this is these ones. And the question is, when does a solution x exist? The answer better be always. That's actually what we're trying to do. We're trying to find that x always exists. But this is a little bit strange. And here's something where even if you have studied linear algebra before in whatever context, you generally have not learned how to solve for whether these have solutions. Actually, generally speaking, we learn about ways to calculate determinants, we learn how to calculate ranks. We learn that in certain cases, you know that the solution exists. For example, if A plus I happened to be a non-singular matrix, then I'll be in good shape, right? So this suggests that maybe the way you try to prove this result is you just try to prove that A plus I is a non-singular. There's only one problem. So now here's where there are some challenges. The first challenge is that A plus I is not necessarily non-singular. Okay? Actually, there's a very easy counterexample, an easy example of when this is the case. Can anyone think of a graph for which it's obvious that A plus I is singular? Yeah? two vertices, and I'll say complete graph would be a generalization of that. If you have a complete graph, Kn, which stands for a bunch of vertices, and every possible edge is present, then your A plus I, since everything is adjacent to everything, they're all ones. There are a lot of ones here. They're all ones. Okay. Very good. Okay, so they're all ones. So now, if these things are all ones, this thing clearly has rank 1, and therefore it's actually singular. So this method won't work at all. So then the interesting thing becomes, how can we try to categorize when a matrix equation has a solution? I will say it is now actually getting worse. I'm going to try to unplug it and plug it back in again. We'll try. Okay, we'll keep going. Okay, so now I want to actually study the theory of when you actually can solve such equations. This is actually quite fun. So let's think about the general question. If I have b times x equals the all ones vector, this is the all ones vector, over f2, when does this have a solution and when does it not? Because I need something more powerful. Previously I just said if the determinant is non-zero, okay, then there's a solution. But it turns out I need something better. Suppose your job was to try to figure out if this had a solution. How might you proceed? If you were given E and asked to find out if there exists a solution, and you didn't know any fancy theorem, what might you try to do? So suppose somebody gave you a B, and there's like some numbers, zeros and ones inside. What might you try to do? Yes. Brute force. Exactly. That's what I want to do. You might use brute force. Well, what does brute force actually mean? So brute force means that you would write down, again, this is how I often note this. I would write down a matrix, which has B here, and a bunch of ones. Is this okay? You usually do something like this. And brute force consists of doing row operations. You use you use row reduction. So what you do from here is you do row reduction on this particular matrix. And when you do row reduction on this particular matrix, under what circumstance is there a solution or isn't there a solution? Maybe we should think about an exact example, and then it will be easier for us to see. Okay, so let me make a simpler example that I don't have to have as many rows and columns for. But if I just had something very simple with 4 vertices, 1, 2, 3, and 4, clearly the theorem is true, so I should be able to do it for this. So if I have 1, 2, 3, and 4, then my B is equal to, so I have my 1, 2, 3, and 4. Here are the 4 ones. Now, I made it A plus the identity, so I have these. And I have 1 is adjacent to 2, 2 is adjacent to 1. And then somehow 2, 3, and 4 are all adjacent to each other. I think this is correct. Does everyone believe me on this? Does it seem reasonable? 2, 3, and 4 are all adjacent to each other. The rest are zeros. So if I have a picture like this, now if I attempt to do row reduction, you already see, by the way, that the matrix here on the left, this B, is singular. I have actually 2 completely identical rows. But when I'm trying to simplify this, maybe the easiest way to do this would be to take the second row minus the first row, when I do it on the second row part. And I get 1, 1, 0, 0, 1. This one, when I subtract, I get 0, 0, 1, 1, 0. The third one, let's leave alone for now. 0, 1, 1, 1, 0. And for fun, let's already subtract the 4th row minus the 3rd row. So I have this picture. Is this okay so far? There's a mistake. There's an error, because one of those is a 1. That's important. Okay, let's do that. So that's a 1. And now if I continue, I guess I'll exchange 2 rows. That'll be enough. I'll exchange rows 3 and 4. Sorry, rows 2 and 3. 1, 1, 0, 0, 1. 0, 1, 1, 1, 1. 0, 0, 1, 1, 0. 0, 0, 0, 0, 0. At this point, it's actually clear that this can be solved. At this point, if you actually wanted to go back and figure out what were the values to make into this 4 long column vector, you could find them. And there's a reason why. Does anyone see what makes it so that this has a solution and what might have made it so it doesn't have a solution? So the upper diagonal is how I was trying to make it, right? I'm trying to do this row reduction. The row reduction is always going to make it so that my leading ones, these leading ones which are marked in blue, these leading ones come from different columns as I go down the rows. But I'm going to say, just in the interest of time, there's something very interesting about this last number here. It's a 0. Since that last number is a 0, this is actually okay. Or rather, maybe I should say something that's very much not okay. You would fail if the row reduction gave, that's a B, a picture, well, let me erase that. It would work, it would fail if the row reduction gave a picture where at some point you actually had a row of zeros with a 1. This is actually the key insight. This is actually maybe one of the things I wanted to give as a take home, because what I always think when I organize a talk is, what is a little nugget that maybe you can really take home that maybe you can use somewhere, or maybe you can see what was the interesting thing about the combinatorics and the more advanced idea that came into the combinatorics. This particular thing is about linear algebra over F2. And it's actually about a very fundamental question called, when does a system of equations over F2 have a solution and when does it not? There's a complete characterization, which is actually what this is. The complete characterization is, if at some point in your row reduction you can get a row of zeros followed by a 1, then there is no solution. That's clear because this corresponds to you having combined your equations until you got an equation with none of the variables added together, and the right-hand side is 1. It's not solvable. On the other hand, if you never find this, then it is solvable. Does this make sense? This is actually the criterion. You would fail if you hit this point. On the other hand, if you complete the reduction, but if the reduction completes, and you have no row which is a bunch of zeros, then there exists a solution. So that's it. So now, first of all, do I still have people with me? Okay, so this is cool. Actually, the first time I saw this, I said, I didn't realize you could make this complete characterization. But I want to take one step further. This sounds a little bit hard to use though. So I have a criterion, but the criterion is basically saying there's a solution if there's a solution. Right? So there has to be something else we've got to say here. The other amazing insight is that if you're working over F2, what are these rows anyway? So when you're doing row reduction, any particular row is always a linear combination of the other rows. So there's an important fact here that as you're doing row reduction, well, let me write it on this page. But during the row reduction, every row is a linear combination of the original rows. Indeed, that's actually why this helps solve systems of linear equations, because every equation you get is created from the previous ones. So there's another way to express this condition, which is that there is a solution if and only if no linear combination of the rows gives you a bunch of zeros and 1. Okay? But here's the kicker. What's a linear combination over F2? A linear combination means I took a row, multiplied by a constant, add another row, multiplied by another constant, add another row, multiplied by another constant. All the constants are parts of F2. How many constants are there in F2? 0 and 1. If you multiply by 0, forget it. So a linear combination over F2 is a collection of rows added together. Okay? So now what I've found out is if I'm trying to solve this b times x equals 1 over f2, my criterion for working and failing has to do with whether or not I can collect a subset of rows to add together and make 0, 0, 0, 0, 0, 1. If I can make 0, 0, 0, 0, 1, then it fits. If I can't, it works. How do I make 1 at the end? So again, I said my linear combination is called, I grabbed a bunch of rows, and I added them together, and somehow I got a 1 at the end. Remember, we're solving bx equals 1. How could I get 1 at the end? Odd number of rows. Okay, so I'm writing down this final condition down here. So we now have an if and only if condition, which is called there is no solution if and only if there exists an odd number of rows of B that add to all 0. Did that make sense? This is this case of bx equals 1. This is the precise condition for whether or not a solution exists. And when I first learned this, I said this is not something I've learned from any linear algebra class that I've ever taken. But it's remarkable. It's true. And why it works is basically because of the row reduction. The row reduction says if this thing didn't happen, you would never get a 0, 0, 0, 0, 1, and so your row reduction always works. On the other hand, if there is a way to make an odd linear combination, odd number of rows that adds to 0, well, that just tells me I have a bunch of equations that if I join them, I get 0 equals 1, which can't be solved. Now let's use it on the problem. I'm supposed to prove that this doesn't happen. Again, my B is an adjacency matrix which runs on the diagonal. So now, I need to show that there is no odd number of rows of this that add up to 0. Let's assume for the sake of contradiction, it happens. Assume, for a contradiction, that when I take this A plus I, this has an odd number of rows that add to all 0. This is an A, so it's add, not odd. Okay, so I have an odd number of rows that add to all 0. Let's look at them. Without loss of generality, there are 3 of them. That's not true. But without loss of generality, there's an odd number of them. I can only draw 3 numbers, right? So there are some 3 rows here which are of interest, and they add to all 0 when I try to add everything together. I now need to find a contradiction saying that there's no way they could possibly add up to all 0. And at some point, I probably need to even use graph theory. This thing came from a graph that I pressed some buttons on. And the interesting idea you can use here is you can say, if those are the 3 rows, let me look at the exact same columns. So these are the 3 columns corresponding to those 3 rows. Remember that the matrix is symmetric in some way. Okay? Effectively, what I want to do is I want to focus all my attention on the 3 vertices corresponding to those 3 rows. And just look at all the action right there. In particular, I can tell you what some of the entries in this sub-matrix that they create are. For example, this is a 1. That's because A plus I put 1 on the diagonal. This is another 1. And this is another 1. And here what I've done is I've focused all of my attention on the rows and columns corresponding to those vertices, those odd number of vertices. But the fact that if I try to add everything together, I'll get 0, means that if I added this number, this is a square, plus this number, I get 0. Is that okay? I mean, that's saying that I added those 3 particular numbers. I'm supposed to get a 0 on every column if I added together these odd number of rows together. But in particular, that column is interesting, because that tells me that the sum of the others is equal to, well, I'll write congruent to 1 mod 2. That means odd, right? When I say others, my others here are the other boxes. Okay? So what I've found out now is that, yes, this is one of my vertices in this odd number of vertices, which correspond to the rows, and the sum of the other entries is 1, 1, 2. What does that mean in graph theoretic terms? These are vertices A, B, and C. Let's call them A, B, and C. They actually are some graph. A, B, and C. And what does this statement translate into about A? In terms of A, B, and C's relationship with each other. Yes? If it's connected to B, it must also be connected to C. Actually, I want the exact opposite of what you said. Because, well, I mean, it's okay. It's going to be one or the other, right? But the thing, no, I mean, like, this is how I solve problems too. It's got to be one or the other, so let's try, right? And the deal is, if I was to add up along that column A, the 1 plus the blue box plus the blue box is supposed to zero out. Therefore, the sum of the blue boxes has to be odd. And what that means is in this graph, the degree of A is odd. Odd degree in the A, B, C graph. Is that okay? Actually, this is a big problem. Because what else do I have? If I look in the B column, I again have an odd number of things, but they're supposed to add up to 0. Therefore, the sum of the other stuff is supposed to be 1. It's supposed to be odd. So therefore, in the B graph, in this ABC graph, the degree of B is also odd. How about C? It's also odd. How many ways do you know to make a graph with 3 vertices, all of whose degrees are odd? It's actually impossible. The sum of the degrees in a graph is always even. The sum of the degrees is like if you had a bunch of people shaking hands in the room and everyone shook an odd number of hands and there was an odd number of people, you'd say someone was lying. So that's just because if you count the number of handshakes, that's exactly twice. Twice the number of handshakes is the sum of all of these handshake counts. And this actually generalizes even if there aren't just 3 vertices. Does this make sense? If I had an odd collection of rows, well, I have a huge problem, because the odd collection of rows would give me an odd number of vertices, inducing a subgraph with all odd degrees. That's bad. So that implies that there exists a subgraph with an odd, this odd is the same as that odd, number of vertices, and all degrees odd, which is impossible. And that actually proves Sutton's theorem, which says that, okay, so therefore the number of ways that you can, there is a way to press buttons to turn on all of these lights in the room, which is remarkable. It works for every single graph. Now, to finish all of this, let's tie this back to what this has to do with the Olympiad problem. So the Olympiad problem was not about pressing some buttons and turning on some lights. The Olympiad problem was splitting people into 2 different rooms. And what does this have to do with that at all? And this was the remarkable observation of Pierre Caro, which is that you can actually use linear algebra also to think about that question where you have people being split into 2 parts. So let's try. Let's now, oh, by the way, let me go back. Did this sort of make sense? This thing? Okay, now let's go back. And now we're not going to use any more of that linear algebra part. We're just going to use this idea, and maybe with a little bit more. So now I want to think about how you split people into 2 rooms. In order to do that, I need to, again, think about maybe having some kind of an adjacency matrix. And I also need to think about how I'm storing who's in what room. So let's do this. Suppose I have a graph. And the graph is going to give me an adjacency matrix. So this adjacency matrix is going to have 0s and 1s, and I'm not adding the I yet, or maybe I will, who knows, of what's going on with a vertex towards itself. But I have this graph and it's an adjacency matrix, and I want to think about trying to write some kind of an equation. So I might want to think about multiplying this by some kind of a vector. Except that now I'm thinking about splitting people into 2 rooms. What might be a reasonable way to think about this vector? 0s and 1s, what does a 0 mean? You're in the 0th room, or you're in the 1th room. zeroth and first root. Yeah, you said the first and the second root, but you mean the same thing, right? So it's like you have room 0, room 1. And if you have room 0 and room 1, you're just going to say, all right, this just means something, right? If I write something like this, this solution x would mean that I've put the first person in room 0, the second person in room 1. I should probably index my people 0 index as well when we're at this. But anyway, that's not actually relevant. So if I want to think about this, I want to think about what does it mean? What would I want to write as my equation that would tell me when I'm done? Does that make sense? I want to think about how to write down a condition for being done. But what would that mean? Let's see. That's a question mark. What would it mean to be done? Now I need to know what kind of an equation would tell me that I've properly split these people. For this, we might need some case analysis. Let's look at the first row. Let's look at this first entry right here. And that will be interacting with the first row. I'll be doing some kind of a matrix product, right? What is this actually counting? If I multiply these things together, my zeros and ones are, when I multiply by the adjacency matrix A, it's actually counting meaning whenever there's a 1, it adds. So this is actually counting how many vertices adjacent to 1 land in room 1. Maybe let me do an example that's so not too quick. Right? So suppose let me draw the same thing again. If I draw the same thing again. Oh, it looks like I have more vertices. Let's add one more. Okay? 1, 2, 3, 4, 5. If you have 1, 2, 3, 4, 5, then in this very first row, 1 is not adjacent to 1. 1 is adjacent to 2. 1 is not adjacent to 3, or 4, or 5. And so when I multiply these two things together, I happen to get a 1, because when I'm multiplying matrices, I'm specifically looking for when is there a neighbor of 1 who's also highlighted with a 1 here. Okay? So this particular entry here is counting the number of neighbors of vertex number 1 that are in room, let's call it group 1. Because I have group 0 and I have group 1. Does that make sense? Now what do I actually want? That's maybe what I want, maybe not what I want. In fact, this is the ugly case. Because I only know that this is 0 in there for the x. I would like to be able to write an equation that somehow says, this means I would like to say that this tells me that I'm done. Except that when I put a 0, if this first vertex is in room 0, why does it even care how many of its neighbors are in group 1? Because it's in group 0 right now. But you can fix that. If only I knew something about my degree in the first place. Okay? So if that's the case, if I knew, but if you knew that the degree of vertex number 1 was even, what would you actually want? If you knew the degree of vertex number 1 was even, would you want this yellow thing to be 1 or 0? So his total vertex is, say, even. And you want ultimately to say that he has an even number of friends in his group. So if it was even, you would want that the yellow thing is 0. Is this okay? If the degree of vertex 1 was even, then you want that this is equal to 0. And if the degree of vertex number 1 was odd, then you want that this is equal to 1. Does that make sense? Because it has an odd number before, and this is going to eat up an odd number in the wrong group. Okay? If statements are very bad from the perspective of linear algebra. This is not an arithmetic statement, right? So this is very, very troublesome. But this is still interesting because it gives some hope. You see, on the one hand, then you could say, maybe I can just try to solve the problem for the case where all the degrees have the same parity. Right, I'm trying to write down the condition here. I'm trying to write down the condition for the right-hand side such that I would love to show that there's a solution. That's my goal. I'd love to show there's a solution. And if only I could make a nice assumption that all my degrees of the graph are even, or all my degrees of the graph are odd, then I'd be done. And if I'm trying to show that there is a solution, it's probably easier if I just say, I know how to categorize how to find out that there's a solution if the vector on the right is all zeros. That's the easiest one to do. So maybe I should just do the case where all the degrees are even to begin with. Well, of course there's a solution. You just put everyone over there. Unfortunately, that was useless. The problem was called, I have this group of people, I need to split into two parts so that one side, all the degrees in their own side are even. That's way too easy. So unfortunately, we can't do that. Instead, it turns out the second one is the one that's interesting. So the idea of Yarantaro was, let's take the graph we're given with and mess with it so that all the degrees turn odd. You can actually take any graph and add some stuff so that all the degrees are odd. This is actually very easy. Watch. Here's a graph over here, 1, 2, 3, 4, 5. If I want to make all the degrees odd, I just do this. 1 is already odd. 2 is already odd. 4 is already odd. 5 is already odd. Oh, there's 3. Let's just add another vertex. Call it 3 prime. Okay. By the way, in general, if I want to make all the degrees odd, I just add some hair coming off of every single vertex which has even degree. The hair is called one vertex coming off. In this case, it's particularly simple because it's just 1. But why is this useful? Suppose I stare at this thing. Now if I have this, I would like to know something about what does partitioning these 6 vertices into 2 groups have to do with partitioning the original 5 vertices into 2 groups. And the key insight is there's a one-to-one correspondence between every partition of the 6 vertices into 2 groups where all degrees in your own group are even, and every partition into 2 groups of the 5 vertices. What? If you partition these, actually now I have to think of what the partition might look like. Let's see. So here's a way to partition. Actually, here's what you do. You'd say, vertex number 1, it has degree 1. If that's the case, then wherever 1 goes has to be on the opposite side of 2. Does that make sense? This is the key insight, actually. If you have a vertex with degree 1, then it must be on the opposite side of whatever else it's connected to. So 1 is opposite of 2. Now 2 is adjacent to 3 and 4. Should 3 and 4 go on the same side? There might be many partitions, so let's just put 3 and 4 on the same side. If 3 and 4 are on the same side, I have this. Now 3, I'll put 3 prime over here, and 4 comes across the 5. And I have created a partition of these 6 vertices, where in each side, all of the degrees inside that side are even. Do you buy this? But look, how do 3 and 3 prime compare? They're always on opposite sides. That was why I made this comment as I started, saying, if I have a vertex of degree 1, it has to be on the opposite side of its partner. The key insight here is that this shadow of 3 prime, is always opposite of 3. So there's actually a one-to-one correspondence. All of the partitions of the 5 vertices satisfying the property are in a one-to-one correspondence with all the partitions of the 6 vertices satisfying the property. Where all I do is that the prime vertex is just thrown into the opposite piece. This works even if I have more than 1 even degree vertex. No matter how many even degree vertices, every one of them gets a 1 degree vertex dangling off. And if only I could solve the problem for this all odd degree case, then I can also solve the problem for the arbitrary case. Furthermore, the number of ways to partition is also the same. So the problem now reduces to saying, can we solve the problem for the case where all the degrees are odd? What's that? That looks familiar. If all of the degrees are odd, then I would like to be able to solve this system of equations where the right-hand side is, oh, just a second, I need to say one more thing. Right, so if I want to say if the degree of vertex 1 is odd, then the right-hand side is supposed to be a 1. But what happens in this question? So now here, if I now know that every single vertex is odd degree, then I know that I want the solution to have a 1 on the right-hand side. On the other hand, wait a second, something is slightly off. If the degree of vertex 1 was odd, if it's a 1, right. So I want this thing to go to 1. Yes, okay, yes. So there's one trick inside here which I need to put on. So in this particular case, if I want that this thing is equal to 1 on that side, that's still not great. Because unfortunately, there's one more catch, which is that if I'm here, and suppose I had a 1 on this one. Suppose this was a 1. And again, as I'm doing this, this is 0, 1, 0, 0, 0. If I'm multiplying these, what would I want to get here? So this is the last case, right? The first case was called if I had a 0, if the vertex number 1 was in group 0, what do I want? I want a 1. If vertex number 1 was in group 1, what I would like is that what we're counting on the right-hand side here is we're counting, this is the number of neighbors of vertex number 1 that are in group 1. What do I actually want this to be? This has to be 0. Yes, this is the inversion that I was talking about. This has to be 0. You want this to be 0. Now, how can I do this? I want to say that I need to have a times x equals something. And the something on the right has to be 1 if I had a 0 in x. And it has to be a 0 if I had a 1 in x. What's this corresponding to? This is adding 1. This is flipping the paradigm. So what I actually want to have, if I want to make this thing work, what I actually want to have is I don't want to talk about a times x. Because what I want to get on the right-hand side is exactly x plus 1, or 1 minus x, either way that you look at it. Actually what I want in this problem, in order to solve this 0 here is opposite of the 1. So these are the key, this is the key that's important here. These two are opposite of each other, right? These two are opposite, and also these two are opposite. And so since they're always opposite, I can address this problem by instead saying that I want to think about what happens if I have a plus I multiplying by a vector. If a plus I multiplies by a vector, and this is the x, let's just do this, right? If a plus I multiplies by a vector x, now what I want, in order to be done, is that the right hand needs to be all ones, okay? So that means people are still with me. Some people are still with me, right? So this thing has a solution if and only if there exists the corresponding partition. Because at this point, since I did a plus I, this helps me to toggle. Anything that was a 0 turns into a 1. Anything that was a 1 turns into a 0. So I just need to know whether or not this has a solution. A plus the identity matrix times x equals to all ones vector. I think we just saw this. This is that previous problem exactly. So this is that problem about Sutler, about pressing the buttons. We are back at it at the same thing, an adjacency matrix of a graph plus the identity matrix equals the all ones vector. We've already proved this works for all such graphs, for all graphs. And therefore, this has a solution. Furthermore, this thing actually then solves the USA Math Olympiad problem, because the USA Math Olympiad problem asks for a power of 2 many solutions. When I have a solution, the solutions all form a translate of a subspace. And the dimension of the subspace is an integer, and we're working over F2, so the number of solutions is a power of 2 as well. So this actually then answers everything. To recap, what in the world happened here? So effectively, this is an example of when the bare hands fail. This is a question where if you try to solve it, it was actually extremely hard. How you would actually try it in the power of 2, many ways to partition, not clear. But to recap what was really going on here, we had to use very deeply this characterization of when does a matrix equation, square matrix times vector equals all ones, have a solution. And the thing to remember, is it corresponds exactly to having an odd number of rows that combine to all zeros. And that gives us a powerful theorem we could use. And then for this thing, this is one of these classic combinatorial tricks, where you say, I have a problem. I don't actually know how to handle this problem for all general cases of graphs. It's very annoying. It depends on whether vertices have even or odd degree. So you regularize everything. In fact, you may even use this sometimes in other work that you do. If you have something that's not nice, you find some easy thing you can do to make everything at least behave uniformly. And in this particular case, it worked well, because if you had a vertex which was only of degree 1, which you added, then it actually has to be on the opposite side of the partition. So then the number of things that you're counting actually doesn't change. And in the end, when we do the matrix product then is extremely nice. It actually comes out to giving you the condition that you want exactly when the right-hand side is exactly the flip of what you had in the corresponding position in the x vector. Whenever you see yourself flipping in F2, that's equivalent to adding 1. And at that point, adding 1 is just like ax plus x, which is a plus I x. So that was the math content. I hope that was somewhat interesting. This is actually something which, when I first came across it, I couldn't believe that you could use this linear algebra in this way to try to solve a combinatorics problem. Definitely, it's not a bare hands approach. But what I've discovered is that if you explain this much more slowly to high school students, it's actually also understandable. Because the only thing that we used, the only rocket science, was called solving systems of equations, which people are used to. Maybe to draw back and close the talk with this part of the talk is just some more things that are maybe more relevant to Maths Olympiad. This is now not so mathematically technical. Let me go back to this. It is because of all of these connections that we actually decided to try to, in say, the US Math Olympiad training, kind of talk about things that might not just be using the bare hands techniques to solve questions. This, for example, is an example of something that we do in the evenings. This guy here is talking about quantum computing. This is at the US Math Olympiad training program. And something that we've done ever since I was a bit more involved in making the program for the way we teach, actually starting around 2008, was to actually have more communication about these kinds of mathematics that you might not expect to see anywhere on an Olympiad. However, it turns out that this actually might have some relevance. In particular, that particular problem that I showed was an Olympiad problem, and there were some abbreviations on the question right before it that said that they were on the team selection test of Germany and Iran, that summer problem. So we do this sort of thing. And these are actually informal evening sessions where somebody talks about what they're actually doing, which might have nothing to do with Olympiad mathematics. And then another thing that we try to do is we try to make sure that people at least find this to be fun. Actually, this room looks sort of like the room that we're in right now, in the sense that it's a performance hall. And one of the things that we try to do is we try to have as many informal, fun activities as we can, so that people can find that working hard on this mathematics is actually also interesting. Actually, they're about to sing. Many people are quite musical. But these are just a little sampling of the kinds of things that we do, hopefully to inspire some questions and to open the conversation to something that does not necessarily just have to be about matrices. On the other hand, I hope that what you heard just now is maybe somewhat interesting in showing that there are other ways to look at questions which may on the surface look like there's nothing else going on. Thank you. I'll do whatever you prefer. If you guys would like to sit down, I can sit down too. I'm able to sit down.
We can do both. Who wants us to sit? And who wants us to pace around?
Looks like sitting with. Okay, that sounds good. Sure. Do I sit here?
Yeah.
I do not.
probably the one question we need to get out of the way first is because it relates directly to the problem we were just talking about. Is somebody said a bit confused with the first part. I thought he showed that the complete graph did not, and then does the question actually come up? Yeah, I think it was basically about the complete graph not needing to invert the matrix, and then in the end you showed that you can nevertheless get the vector with all ones. So can you
sure
apparent contradiction here?
Sure. Actually, specifically what I was saying is that if you are trying to solve this system of equations, a plus I equals all ones, by saying a plus I is invertible, that is not a good way to solve it, because sometimes a plus I is not invertible. However, you can still have solutions even when a plus I is singular. As an example, if I'm really trying to solve the system of equations, all ones times the x equals all ones, I can tell you a solution. You make x be 1, 0, 0, 0, 0, 0, 0. And it works. So the bottom line is that there are solutions, but essentially what I was saying is that although it's a sufficient condition for a plus I to be non-singular, that's not a necessary condition. And that's why we dove into all of this work to try to find a necessary and sufficient condition, because that would actually achieve the goal that we wanted.
I think you kind of set yourself up for this one. What is Ramsey theory?
What is Ramsey theory?
Set you up for this one.
Yeah, sure. Okay, so I'd say that there's a colloquial way to say Ramsey theory says that complete disorder is impossible. Let me make an example. So here we maybe have about 200 people. So if you look in this room, there's definitely some 6 of you who are all already friends with each other on Facebook. Or, if there is no such 6 of you, there are some 6 of you who are not friends on Facebook. All not friends. So what I'm saying is, there exists some 6 where there are 0 or 15 friendships among you on Facebook. And it could be both. There could be some 6 people who I've never met, and there could be some 6 people who are clean. But this is what Ramsey theory is talking about. Actually, there's a funny story about this, which is that, again, this is maybe folklore, and not exactly true, it's these urban legends, but that one of the first people who thought about this particular result was a sociologist who was observing classes of about 20 kids and observed that somehow among 20 human children, you would often find 4 people who were already played together, all of them played together as pairs, or you would find 4 people, all pairs never play together. And instead of submitting this as a sociology research result, fortunately this person was Hungarian, and he realized that this was actually true even of ants. This was true of any time you have 20 vertices. So Ramsey theory, roughly speaking, is if I have a very large system, what must happen inside it, no matter what?
Maybe one other question which receives quite a lot of upvotes, even though for some reason it's just disappeared from the app. But I think since you showed a picture of all average, it's surprisingly large number who wanted to know the average number.
Oh, okay. So, I mean, my average number is 2, but that's also because I work on this area of mathematics. So, you would expect that your number is around 2. It's hard to be 1 at this point. Oh, in case you want to know what this means, Erdős has an Erdős number of 0. Erdős's collaborators, anyone who co-authored a paper with him, has 1. He unfortunately has passed away, so it's very difficult to get 1 at this point. Now 2 means that you have co-authored a paper with one of his former co-authors. So yes, I have a 2. But that doesn't mean anything about your mathematical ability. it just means that I work in this circle. Yes.
Thanks. Going back to the question you went through, how many people actually managed to solve it during the test?
On that one, I don't recall. I only recall it was considered extremely difficult, because nobody was expected to use the linear algebra solution. In fact, nobody who was proposing it knew that that existed. So actually, I just came to help grade the exam, and I said, oh, this is cool. This has this whole linear algebra stuff behind it. And everyone said, really? Right? Because they knew how to do it with some induction and counting, and it was horrible, right? Horrible meaning horribly difficult. I don't recall how many, but I do remember that this was considered extremely difficult. Right.
I think somebody else actually did explicitly ask whether you knew of a solution that didn't involve linear algebra. So I guess you
Yes.
But is it possible to sketch out the solution, or is it really so horrible that we better not talk about it?
Yeah, so to be honest, solve it? Where do I learn something from? Actually, I should tell you, as I was preparing this talk, I was considering getting the statistic for you of how many people solved it, except that then I realized that was confidential information that I shouldn't open. That's the only reason I'm not telling you. It's because somehow I shouldn't tell you what's in the spreadsheet. But in any case, I will just say that it's known to be very difficult, and the solution was long, and it was not clear where the intuition was coming from. Where the way that I just did it, somehow once you reduce it to this other thing about pressing switches, it's like there is an intuitive path. This one I didn't know how to do with intuitive method.
Well, another question which comes completely from the left field, or rather probably comes from our recruitment team. Would you ever consider returning to finance? So you mentioned Paul used to work for a competitor, who shall remain unnamed.
Sure. I honestly, I thoroughly enjoyed the time that I was working in finance. These days, the answer would be no, but not because it's not a good job. In fact, I thought it was a fantastic place to work. It's just that these days I happen to be, myself, primarily engaged in a lot of this outreach, helping more people think that mathematics is interesting. I find that very fun to do. And so I actually throw my energy into there. And so the answer would be no, but that's only because I'm doing this thing this mission that I'm working on.
Yeah. If that ever changes, you've got a
Sorry, I didn't mean that in any negative way. By the way, I should say I actually thoroughly enjoyed the time that I was working in finance, and I could have entirely seen myself being very happy in that regard. It's just that because I've already started something with momentum that's helping to promote this mathematics, I must finish what I started.
I'll slightly generalize the question as given. The question was, do you think raw competition math skills help with investment research? Or maybe any other interesting aspects?
Okay, what does raw competition math skills mean? I'm going to take the liberty of interpreting it in the best possible way. And what I mean is I'm going to interpret raw competition math skills as not trained competition math skills. Raw, I would call the wits to problem solve, to say that the screen is flashing, let's unplug it and plug it in again, darn it. That kind of raw math competition skills is useful in many contexts. And now I'm differentiating that from the trained competition math skills. Some people will say that competition math only has these kinds of questions in it. Let's go and spend 3 years completely analyzing to death all the kinds of math that's inside here and become a professional competition mathematician. That would be very good at competition math. Your question was, is this applicable elsewhere? You'll have learned lots of things that are useful for competition math. Some of them will be useful elsewhere. I actually did competition maths in the late 1990s when you couldn't Google anything. There was no Google. If you wanted to learn how to do this stuff, you just used your raw wits to throw yourself against questions, and you didn't really have much theory. I feel that everything I learned from that experience has been extremely portable, in the sense that then I went on and did research mathematics, or these days coming up with weird ways to help people in the world think that math is interesting. These general skills were very useful. So I'm going to then, my answer to your question is just the professionalism inside the maths competition world, that is not as necessary, in my opinion. I think that using the maths competitions as a way to develop your creative problem-solving ability, that's really valuable.
Yeah. So just trying to decide whether to take the obvious question or another sort of quirky left field question. That's not really obvious.
Quirky left field.
Yeah, okay, let's quirky left field question as a quickie. Somebody actually asked, what is your favorite field in which you're doing algebra?
So I would say I'm partial to F2. I think that F2 is very, very remarkable what you can do. And just the amazing thing to me was linear combinations over F2 are just sums. I mean, that was just surprising the first time I thought about that. So there's a lot that you can do in F2, so I do that. In the world that I work in, we don't work with complex numbers too much. When I count things, they're usually real. So somehow C is cool, but I just don't usually need C. F2 is great. Okay.
That answers the question exhaustively to whoever asked it. Right.
So, one people, presumably a parent, asks, does your experience of teaching maths Olympiad students help you to, do you have advice based on that about teaching children, G5-year-olds?
Yes. So the first advice is that I don't teach my own kids, I only teach other people's kids. I should be a little bit more careful with that answer. I mean, my wife actually teaches our kids things. But what I've always done is, easier for children to find math interesting if there's a group of other people who find math interesting. So actually, what I did is I went to the school that my kids go to, and I taught all their friends. It's like if you're playing basketball, you can try to make a swish shot of just going into the basket, or you can go off the backboard. So this is the equivalent to going off the backboard, where you say, let's just have tons of people from this school think that math is interesting. Then you achieve the same goal. Now, if I wanted to give advice on teaching five-year-olds maths, that's actually what my professor has done a lot of. And I'll just say one of the interesting techniques that I watched her use, which I thought was very interesting, which is not to memorize your times table, or not to focus all your energy on memorizing the times table or your addition table. I witnessed as when they were teaching, like, how do you remember what is 5 plus 6? A lot of people would just say 5 plus 6 is 11 because I memorized it. I watched her have our kids not ever remember 5 plus 6 is 11, but they puzzle through it. They say, well, 6 is after 5, so it should be after 5 plus 5, which I remember was 10. This reduces the amount of memory from quadratic to linear, right? So it becomes linear plus a little bit of problem solving. Like if you want to do 4 plus 6, you might need to move some stuff. Like 6, you take 1 out to 6, drop it down to 4. Oh, it's 5 plus 5. I knew that. But then we would watch as our kids, as they're stumbling through single-digit addition problems, they're moving numbers back and forth, they're going forward and back, they're learning how to solve problems. And then the other day when our youngest was learning multiplication, I heard my wife ask us 4 times 6, and our daughter took half a minute to respond. And my wife said, why? Not why so slow, but why? Why? And the answer was, and she always asked why, whether it's right or wrong. And the answer our 5-year-old gave was, well, because you take 4 times 6 is adding 6 together 4 times. So you do 6 plus 6 first, you get 12. And then you do 12 plus 12, and you get 24. That's better than memorizing 4 times 6 is 24. Because you actually puzzle your way through things. You learn that repeated doubling is times 4. There's number theory, there's algebra. So my answer is, don't do things the normal way. If you can always find ways to inject problem solving into teaching the simplest of things, then you learn how to think from the beginning.
Somebody has a very terrible question. What software are you using for the dartboard?
Okay, so as you can tell, I run Linux. I was using a software program called External, X-O-U-R-N-A-L, except that I needed to download the source code and change some things. Because I had a very specific use case I wanted, and I wanted to adjust maybe some colors, some layouts, some icons shouldn't be there. And so I basically took the open source External, X-O-U-R-N-A-L, downloaded the C code and edited it and recompiled it. So that's what I did. It's not actually that hard. I'm serious, it's actually not that hard. All of you could probably do it too, anyone who wants to do that. I love how Linux has open source software, so whenever you need to make your own changes, you do. Actually, the summer I was working at the other hedge fund, at some point I needed to have a spreadsheet which had, it was like a dimension, I'm not saying anything confidential, but I'm just going to say, and it was a high dimensional spreadsheet. And at the time I was working there was a limitation to Excel where it could only have 256 columns. But fortunately, you could download the source code for numeric and just change the hard-coded constant of 256 to like 16384 and recompile. And so I found this very useful. So this is a random tip. Today, all of the modern Excel, you should have more than 256 columns. But that was for like maybe in the mid-2000s. I was doing something for this other firm where we needed to have large spreadsheets. And so we just recompiled it.
Yeah, I guess the sort of obvious question also to earlier was, I think quite a few people were sort of asking for what your sort of secret was in sort of somehow improving the performance of the US team, the IMO for such a short period of time so dramatically. So, and that question was actually repeated 2 or 3 times in very similar ways. So I think a lot of people are curious.
Oh, sure. I mean, I would say the first key is to inherit a really good team. It is not true that I improved it dramatically. Before, the US was also placing second and third. Third, second, and first are not that far behind. Right? So it's just that it was maybe more newsworthy because suddenly it was first. I can say there were a few factors at play. One is that the internet was invented. This changed how people learn dramatically. And in fact, today, whenever I work with high school students, I'm shocked by how many of them have learned the combinatorial with Stellensatz before they show up. I came across this result when I was a PhD student. Okay, so it's just that these sorts of knowledge have propagated over the internet like fire. And that's one of the things States, many of the students actually spend a lot of time on the internet self-teaching. So that's one aspect. I'll say another thing that happened is I inherited an amazing team in 2015, which happened to really want to place first. Somehow you have to really want something and try very hard to achieve it. And they did, they placed first. And thereafter, everyone in the US team said it's possible to place first. Because before that, a lot of people had thought that placing first is out of reach. It's like the 4-minute mile. Once somebody ran the mile in less than 4 minutes, suddenly lots of people broke the record because it broke the psychological barrier. And I'll say that even today, when our team goes to the International Math Olympiad, they no longer go in just with the goal of individually winning gold medals. So just to maybe talk about some of the technical details of this competition, you can usually win a gold medal in this competition by solving somewhere between 4 and 5 problems out of 6. If you solve 5 problems out of 6, you're in good shape. Sometimes you can get away with 4 plus fit. But that would mean that in the past, if you have done the contest problems and you have solved 5 questions, your mental state becomes, I got my gold, right? On the other hand, if you want to win the competition, you have to solve 6 problems. So you see, what I'm trying to say is that there's an additional step. If your actual goal is that your team places first, not just that you walk away with a gold medal, you have to solve that 5th question and say, now I'm going to go for 6, as opposed to saying, my job here is done. And so I would say that these are the dynamics that I have nothing to do with, that I just inherited. I try to at least make things fun. I mean, I try to show some interesting ideas. I actually gave this entire problem that I just talked about here, I taught at our Math Olympiad training program this year, just to show how the kind of problems that they're working on can have some relation to things later. And I also try that, I try to make this so this is a fun thing to do. And I'm supported by the Mathematical Association of America, which is the non-profit organization in the US that runs all of these competitions. And they also believe that this is the right way to do things. So somehow between us in this collaboration, we try to let people who are working towards these Math Olympiad goals see that they're moving towards something much bigger.
You mentioned in your preamble that a good way to learn a subject is to get a textbook and do every problem from it. Are there any textbooks that you think you would recommend people do that for fun and enjoyment?
So for fun and enjoyment, there's actually this remarkable book by Loda Alone and Joel Spencer called The Probabilistic Method. That's actually a book that I also, actually my PhD advisor requires all of his students to do all the problems in that book before you work with them. But this is a book where the problems are all unique combinations of combinatorial ideas and some probabilistic ideas. The problems are very hard, and that's why they're great challenges. Yeah, I would put that one there, because it blends a few ideas together.
Also, I've seen that some of the people involved in the organization here are sort of gently, subtly co-working, tapping at the watch. So I think it's probably time to draw this to a close. I mean, of course, Paul will be around for a little longer, the Prince reception afterwards. But don't clap just yet, because there's one last thing I wanted to do before we all disappear. And because you mentioned the lights out game, it's especially for you, off eBay. In this year back, there's a special present from G Research. Genuine 1990s lights out games console, and maybe over drinks.
And it involves turning lights and toggling them or something.
Yes, it has the most awful beeping sound as well, so I wouldn't do this anywhere near your microphone. But
all right.
So the small token of appreciation.
Thank you.
And, thank you very much for a fantastic